Hi everyone, this is Will. Welcome to miniKanren Intro Hangout. I guess I'll call this Hangout number 9. We actually had a Hangout last week, which was sort of an informal Hangout where we solved some problems and asked and answered a bunch of questions about miniKanren. We decided not to record that just because didn't want to put anyone on the spot for asking questions or solving all these problems, but I think it helped people out. We could potentially do some more Hangout sessions for problem solving, or come up with another way for people to ask questions and solve problems and so forth, if people are interested. If so, let me know, or post a mailing list or something like that, and we can try to arrange some special sessions, maybe at a different time if that's more convenient for people, or can post some problems online for people to try, or whatever it is. Try to do something like that, or people could post some questions and I can respond to those, or other people can maybe have their takes on those questions. I'm not sure. Anyway, so that was what we did last week. This week we're back to miniKanren, and we did 2 weeks ago for Hangout number 8. We did things like rember-o, I believe it was, and member, and we got into disequality constraints, all those sorts of things. So we're going to do some more recursive functions today, and we're getting closer to writing our relational interpreter. Right, so we're kind of going up, getting closer and closer to being able to write something like our eval expert interpreter from before that we wrote in Scheme. We want to be able to write that in miniKanren and see all sorts of neat things that it's able to do. So let's write some more recursive relations. See if we can do something a little more fun than member today. Right. Let's share my Emacs. Okay, so I loaded the miniKanren files at the top of my hangout9.scm. And so what sort of problem, or what sort of program should we write? I don't know. I feel like maybe writing something a little more fun. Instead of dealing with lists, so we worked on rember, which takes a symbol in the list. Sorry, we worked on member, which tells you whether or not a symbol is in the list. We could do something that returns a list. So I don't think we wrote rember, did we? Did we write rember that removes an element from a list? That could be a good warm-up if we haven't. I don't think we wrote that. Am I correct? Correct on that. I can always look at the file. Yeah, I don't think we wrote that one either. I think I remembered. So we can write rember, and then once we've warmed up with rember, then we can write something a little more advanced. And I've got maybe a fun one in mind. All right, so let's just go to Scheme. Does Scheme have rember? Oh, doesn't have rember. Okay. There are some variants that I think are built in, but so let's just define in Scheme what rember is. This is sort of a standard little schemer type program. So here's what rember is going to do. Rember is similar to member. So if you remember member, our member would take a symbol like X, and it would take a list. And it was a predicate. It was going to return true or false. That kind of thing, right? So that was member, or member, huh? Rember is going to be a little similar. But what it's going to do is it's going to remove a member. So here we're going to remove the first occurrence of X from the list. And the way the standard member, the way Dan normally writes it, works is like this. So rember really is only going to remove the first occurrence of the symbol from the list. And if the symbol doesn't appear, then we just get back something equivalent to the original list. And of course, if we try removing something from the empty list, we just get back the empty list. Okay, so that's how rember works. Okay, the main thing to keep in mind with rember is that we're only going to remove the first occurrence. So this example is one to keep in mind. And we can change that behavior. We can remove all the occurrences later, but let's start with this version of rember, okay? All right. So let's just write rember and scheme to begin with. So we have, some symbol X, some list ls. And we have some con clauses here. So we know we've got a base case. So the one question is, is this going to be recursive? Yes, it's recursive. What are we going to recur on, X or ls? Well, X doesn't have any structure, it's just a symbol. So we have to recur on ls. And so when we're recurring on the list, what do we do? Well, we check the base case to see if the list is empty. Okay, that's fine. What do we do in that case? Well, we have an example that shows us. If ls is the empty list, we just return the empty list. Or we can return ls here because we know ls is empty. So either way, write empty list or ls would be fine. That's our base case. So what decisions do we have to make? Well, if ls isn't a list, we know it's a pair. Okay, so that means it has a car, has a first thing in it. And so we can ask whether the first thing in the list is the symbol we're looking up. Is the first thing in the list y, for example, or we're removing y from y. If the first thing in the list is the thing that we care about, I can write an example like that. If the first thing in the list, if the car of the list is equal to the symbol, then we want to remove that. Okay, and then we're actually done. There's nothing more to be done. We don't have to, because as seen in this example, in this particular example, if we remove X from the list, then we're going to just return the rest of the list from that point on, even if there's an X in it. Okay, so that's fine. We're done. So the key is we want to know if equal or EQB, first thing in the list is equal to X. So just remove that element by returning the rest of the list. That's it. Else, in else case, it means that the symbol we're looking up isn't the first element in the list, like here. Okay, so what does that mean? It means that we have to recur, and furthermore, it means that we're going to have to come back on the first element in the list. We don't want to lose it. Okay, so we can go through. That's one way to think about it. There are a couple of ways of thinking about this, right? We also see this way of, write the recursion first. And so we write recursion. We haven't asked any questions about X, so that X stays there. We have asked questions about ls. We have to get ls closer to the base case, which is null, which means we have to take the quitter of ls, right? So that's our standard reasoning. And if we just got back, well, we can play computer, try some examples. If we just do the recursive call, and what we'll see is that in a case like this, the answer that we get back would be missing the y at the beginning. Okay, so we have to remember to cons on the car of ls. So hopefully at this point, the process that we've gone through is standard for you, right? So try this out. Remember, great, and try a couple tests. And as some people have pointed out, we absolutely could be using, some sort of test harness or test framework or whatever, unit test framework, whatever you want. Right now, I'm just, for the purposes of trying to go through these simple examples, just trying to illustrate this manually. But obviously, if we were writing more complicated code, it'd be important to have test cases and all that. So let's see, do we just check manually? Did we get the right answers? The answers we expect, at least. Looks like we did okay. Okay, great. So we have what appears to be a working version of rember. And now we want to have the equivalent of rember written in miniKanren. We want to write rember-o. That's the miniKanren equivalent. So we're going to define rember-o. Rember-o is going to do the same sort of task as rember. And because we're writing rember-o as a relation, and we want to be able to reason about, sort of the list that would have been returned by rember, this is where I can type out, but Louise will object because out's not a very good name. So I guess I can say ls minus x. I'm not sure what a good name is. It's sort of the list minus the first occurrence of x is really what you're getting. So I call it ls minus x, just instead of out. I don't know. Naming things is hard. So instead of con, we have con-d. Or it could be slsl. Oh, okay. All right, Orchid's got an idea. So Orchid has another idea of naming. So it could be sls L. I guess it, yeah. Yeah, I'm not sure what the, I guess the reason I like the XLS is that it matches the original, at least. And that's why I call it out, because I'm lazy. I don't know how to describe it, right? I don't know. I'll just do this for now. I'm not sure. Obviously, there are many ways you can name it. Out is fine, Orchid says. Well, yeah, this is why I call it out. All right, so we have a con-d instead of a con. We're going to have 3 clauses probably, right? We had 3 clauses before. So let's work through these, right? So we have the null test is list null. Well, how do we do that? Well, we could do something like in the first edition of the reason schemer, where we do a nullo. We could define a nullo predicate, but nullo is really just going to be equivalent to that. No nullos, that's right. We could just use a unification. We don't really need nullos or any of that kind of thing. So, nullo, caro, cutero, those are just calls to equal, right? So let's just do it directly. And the thing to keep in mind, of course, is that if ls is coming in as a fresh logic variable, this will end up unifying ls with the empty list. So ls will become associated with the empty list. If ls already comes in with a value, then this unification will fail unless ls already has the value of the empty list. Okay, so that's how we work. It's more general behavior than null question mark. All right. So if that succeeds, if this goal succeeds, the unification succeeds, then in the original version of the code, we're going to return the empty list. But now, of course, in rember-o, there's no notion of returning. There's only associating this out argument, the third argument here, the new argument we just added, with the value that we would previously had returned. So I'm going to unify with the empty list. Okay. All right. So that's the first line. That was pretty simple. Or anything complicated. So that's a very simple transformation. Okay. What about the EQV? The EQV is, that's like a type of equality. Well, when you think equality, one way we have of doing equality is equal, right? In fact, that's our big hammer. And we want to know if the first thing in the list L is equal to X. Okay, so we're trying to see if those two things are the same. Well, once again, that's going to be called an equal. So we have to have some way to get our hands on the car of LS. And you might think, well, maybe we can just translate it like this. But that doesn't work. And why doesn't it work? The reason it doesn't work is that LS might be a logic variable that hasn't yet been given a value. We could have written something like, some call to fresh. We get a variable. We pass that in as an argument to rember-o. And in that case, in Scheme is going to be taking the car of a fresh logic variable. Scheme doesn't know how to take the car of a logic variable. That's not defined. Basically, we represent logic variables in some versions of miniKanren as vectors, which are like array-like structures. So we're taking the car of an array that doesn't work. That's going to give you an error. You see some error saying, attempt to take the car of a non-list or non-pair or something like that. You get some weird error like that. So we have to be a little more careful. We have to basically pull out this call to car and treat that separately. And so this is what we call an unnesting operation. So you can see that we have nested calls up here, nested procedure calls. We have a call to EQV, and inside of that call, in the position of one of the argument expressions, we have a call to car. And in our miniKanren code, we're never going to have that sort of nested call structure. That's not allowed. So we have to unnest this expression. Okay, and so we could unnest an expression like this in Scheme. So, if another way to write rember, if we want to think about unnesting, another way to write rember is we could unnest this call to car and call to EQV in the following way. We could say, well, we want to, the car call comes first. So we could say let A be the car of LS, A being the middle letter of car, B for middle letter of cutter. And now I can replace that call to car of LS with A, the variable reference A. Okay, so this is equivalent. It's fine. I can just do that. So I still have my call to car of LS happening first, just like it would in the original code. The car of LS happens before EQV gets called. And then I'm just giving a name to the resulting value. I'm calling it A. And now I can just pass in A, this variable. And notice that now the call to EQV is simpler. It doesn't have a procedure call inside of it. It only has a variable reference. So that's what we're going to do. We're going to make sure that in miniKanren, all of our calls to equal, for example, do not have procedure calls inside of them. They don't have other calls to equal inside of them, anything like that. That's not allowed. We're only going to have things like quoted values or constants like 5 or variable references inside of our equal. Okay, so we're going to have to unnest these expressions. So this call to car of LS is no good. And we're going to have to metaphorically do the same thing we did up here where we pulled out the call to car in a let. But we don't have let in miniKanren. Instead, what we have is fresh. Fresh is a little bit like let. So I can say fresh A, just like I'd say let A. So now fresh A is a fresh logic variable, right? And what I can do is I can say, all right, we know that we want to take the car of a list, LS, right? So I know that I can use equal. to deconstruct a list. I can use the construct a list. I can use the deconstruct a list, similar to the pattern matching and how we can deconstruct a list. So I could cons A onto D, let's say. So that pair will let me associate ls with the pair AD, and therefore A, the logic variable A that I just introduced, will be associated with the car of ls. And this works even if ls doesn't have a value yet, if ls is fresh. If ls is a fresh logic variable, then ls will become instantiated to a pair of logic variables. It'll get a little bit of structure associated with it. I need to be careful, of course, to have D associated also, because I'm taking cons of consing A and D, so those both have to be fresh logic variables. But as long as I'm just consing up logic variables, that's fine. And remember that cons safely works with logic variables, unlike car and coulter, because cons doesn't have to inspect its arguments. It doesn't have to say that, oh, this had better be a pair or something like that. It doesn't matter. The other way that we can write this expression, or at least one other way, is with the back quotes and commas. That's equivalent to the cons, all right? And so I'll probably start writing the patterns in this way from now on, just because as we get more complicated patterns, just like with pattern matching, as we get more complicated patterns, like once we got into an interpreter, having the pattern matching became more and more useful. It's the same sort of thing. Once, as we get more and more complicated patterns, using the back quotes and commas is going to become more and more comfortable, or more and more. It's going to save us writing more and more code, and it's going to actually make it easier to read once we get into things like a relational interpreter. Okay, so I'll probably start using that format. Okay, so at that point, we've broken apart ls. We know that we have the car and the coulter. And now I can associate the car of ls with x. Okay, so that's similar to my EQV call to see that a and x are the same. They have to unify. Great. If that's the case, then I want to return the coulter of ls in the original code. All right. Well, so how do I return something? Well, I have to unify it with ls. It's x. I return the coulter of ls. Well, once again, this is nested. I've got a function call inside of my call to equal. That's no good. So I have to do the same sort of thing where I have to pull out the call to coulter, and once again, I can't take the coulter of a list anyway. I can't take coulter of ls because it might be a logic variable. So I could do the same thing I did before. Fresh AD. And now the coulter of ls is D. I can write D there. Okay, and that would work. So that's a correct definition. You'll notice, of course, that I've got some duplicated code. So I've got the fresh AD and in both of these, and I'm doing these two unifications to tear ls apart. Now, I should just point out that these two freshes are introducing different logic variables, A and D. So this A here is not the same as this A here. They're completely different, right? Because still scope. So, but because these really are representing, we really are talking about the cars and coulters of the same list, ls, we can combine those if we want. So that's a transformation we can make that's safe. That's an optimization we can make that's safe. So we can just pull those lines out, and pull them up into the single fresh, and then that's fine. And at that point, we don't actually have to take ls apart twice, right? I can get rid of that. So I can simplify my code. Depending on how I write this, I might also notice, well, actually, I don't even have to say depending on how I write it. Another optimization I can make, or a simplification, is that here I'm saying that A and X have to be the same thing, right? So I want A and X to be the same thing if we're going to, basically recognize that X is the car of LS and then just return the rest of LS, metaphorically, then A and X have to be the same. They have to unify, right? But this is a little wasteful because I'm introducing a new fresh variable A, unifying that with the car of LS, and then immediately unifying A with X. So A doesn't really have any purpose other than to serve as a placeholder so with this unification for X. I can actually simplify this by instead just unifying with X directly. That will say the sort of the same purpose. And if I do that, I can get rid of this clause and I can get rid of the fresh A. So I can actually write shorter code. So this is one way you can write it. But we've already seen that there are at least 3 ways to write this code, and this comes up over and over again with the miniKanren, is that there are lots and lots of ways of writing the same code. And of course, we could swap those 2 clauses around, or the 2 goals around as well, right? So, there tends to be lots and lots of ways to write miniKanren code. That's all basically equivalent. Knowing these simplifications is very helpful because then you can recognize when 2 definitions are equivalent. You can simplify your code in various ways and so forth. Okay, so that's one way we could write it. Just like this. Question. I don't understand why we're returning the cdr. Are these goals not all equivalent? Okay, why are we returning the cdr? Okay, so I guess is the question, why are we returning the cdr in member, or is it about in rember, or is it about rembero? In rembero. Okay, so you see why we're returning cdr here in rember, right? Sure. Okay, and we're just trying to model the behavior of rember and rembero. So the equivalent is we want to return the cdr in this clause. So basically, this is the case where the first thing in LS, the car of LS, happens to be the symbol we're looking for, which means that the third argument, which is going to be this list LS with the first occurrence of X removed, is going to just be equivalent to the rest of the list because we found the first thing in LS. The first thing in LS is X. And the rest of LS is what we're calling D. That's like the cdr of LS. And so the D is going to be the list that has had the first occurrence of X removed from it. And that's what we want to be metaphorically our output. Does that help? I think I'm getting that right. Just don't like thinking about returning. Yeah, I guess that's probably the trickiest part about try transitioning your thinking into miniKanren, is the idea that we're not really talking about returning anymore, right? So when I say returning, what I'm really talking about is sort of the metaphorical equivalent of returning a value in the scheme code, where there we actually return a value. Whereas here, we're really talking about associating with this last argument, this argument we just added, some value, right? So yeah, so sometimes you'll find that my words like return slip into my vocabulary because in some sense here we're trying to simulate a scheme function's behavior, right? And so in scheme we have a notion of returning, and this third argument, the reason we often call it out is because it represents the return argument. So actually we could call it, that might be a better name than out, I guess. Like this is what you would be returned, I guess. Would have been returned is maybe a better name for the argument, I guess. So anyway, that's the reasoning kind of we go through. And of course, once you're used to it, you can do this as quickly as you can type. But it is a mechanical transformation, and it's something that you could write a computer program to help you with. Okay, so, or you could write compile or whatever. But another thing I'll point out is that we've talked a little bit about how cond works and Dijkstra guards and all that sort of thing. And remember that whenever you have a test in a cond line, sort of implicit in this test is the fact that the previous tests must have all failed. Okay, so another way of thinking about the CQV test is that this is really the same as and not null ls CQV, right? If we wanted to be able to swap those two clauses, we would have to add this extra test to make sure that we're not doing things like taking cars of the empty list. So, and in miniKanren, we have to worry about this because all the condi clauses get tried independently. So we need to make sure that that we have tests that are going to protect us from doing things like taking the car of ls, at least if we're in scheme and we want to reorder things. In miniKanren, it's a little bit different because in miniKanren, we can try doing something like breaking apart or pattern matching against an empty list. It just was going to fail. This is sort of like a p match or a pattern match, right? So this unification will just fail. We're not going to get an error or something like that. So the fact that we're unifying ls with a pair means that in fact, this is equivalent to having a not null test or a pair test. Just the unification itself protects us, and so it's no problem. So we don't actually have to have an explicit not null test. We don't really have negation anyway. So this would be more like we'd have to write it as pair. Okay, so we could do something like have the equivalent of pair, but what would pair of ls look like? Well, you could write parse, and in fact, we have parse in the first edition of the Reason Schemer. But parse basically is just this: it's just unifying the list with a pair. So here we're basically doing the equivalent of parse and kutero and kanzo all simultaneously. So we're getting 3 operations for the cost of 1. That's the other reason to use equal instead of using karo, kanzo, parse, kutero, all that sort of thing. So one unification can do the work of several operations simultaneously. So it's much more sufficient, much more, it's much more succinct to write this in this style. Okay, but else is maybe a different beast, right? So else, else is going to say that the first 2 tests failed. What do they mean? So in this case, it means that we know that ls is a pair. Furthermore, we know that the car of ls is not equal or not eqv to x. Okay, that's really what that means. So the else is actually this more complicated test. That's metaphorically what's going on. When we want to translate this else test down here, that means we have to do something similar in spirit. It's easy to assert that ls is a pair. We can do that just through unification. So, that part we know we're going to have to do. This. Okay, so that part already, just by unifying ls with a pair, that's equivalent to asserting that ls has to be a pair. Okay, so that part of the test we've already taken care of. Fine. But the other part is basically saying that the previous test failed, right? That the car of ls and x have to actually be different instead of being the same. So we want to encode that as well. Well, how do we say that the car of ls and x are different? Well, this is why we have that disequality constraint. You can do that. Okay, so now we've said x and the car of ls are different. Okay, so that's really discharging the obligation for that test. And now we can just go ahead and do the equivalent of returning the cons of car ls to the recursive call. So here we actually have to have a recursive call. It becomes a little more complicated. I'll copy the recursive call down. We can see the recursive call right here. Okay, so that's the recursive call that we need to do the equivalent of in miniKanren land. And you can notice right away that we have some nested calls, right? So in fact, this call to coder is inside of rember, which is inside of con. So we have several levels of nesting. So what has to happen? Well, if I pull this expression down, maybe it's easiest to kind of see this in a comment, and we can think about what's going on. Well, you can pull out. We could do something equivalent to having that let binding, right? So A is the car ls, and you could say, D the coder of ls, and then you end up with you're just doing the scheme version, right? So you can pull out the A, you can pull out the D, and now we've removed two of the nested calls. We still have the recursive call though, so we could do something like maybe let the result of the recursive call do that recursion. And now we've completely unnested everything. So rember only has variable references. That call to rember. The call to coder only has variable references. The call to car only has variable references, and the call to cons only has variable references. So there are no nested calls here. We've pulled out all the parts by using let. Okay, so that's what it looks like if we were to do that in Scheme. We are going to do something similar to our code in miniKanren. Yeah, okay, so I was afraid that was gonna be a little confusing. Just to be clear, what I was really showing is in the equivalent to the Scheme version. Okay, so I guess the part that's maybe most confusing about this is if you're doing any sort of translation from Scheme to miniKanren, part of the time your head is in Scheme land, and part of the time your head is in miniKanren land. So what I'm talking about is doing the equivalent of unnesting the Scheme expression. So let's just look at rember first. Okay, we're still in Scheme land. Forget rember-o. We're just in Scheme land. So what my claim is that this version of rember, which is admittedly quite complicated looking, is equivalent in behavior to this version of rember. That's the one we started with. That was quite simple. Okay, so I've got this kind of monster version of rember, which is quite long, and it's been modified in sort of two important ways. One is the tests. Well, okay, so yeah, it's been modified in two important ways. In fact, I need to modify it one more way if I really want to do it right. Sure, make sure I can really. Okay, so it's all right. Let's start over one second. I apologize. So let's just do it for real. You actually can write miniKanren code this way, by the way. This is one way you can write it. What we're going to do is we're going to take rember, our original tested simple version of rember, and we are going to transform it step by step into this kind of bizarre looking version of rember that has certain properties that are useful when we go to miniKanren. Okay, and this will both illustrate those properties and be an artifact that we could directly translate to miniKanren if we want. So one thing we have to worry about, this is just the sort of, this is our simple rember. Okay, this is the original rember. Okay, so now what we're going to do is we're going to add Dijkstra guards. We are going to make sure that every con clause has a test that is unambiguous to the extent that we could reorder the con clauses any way we want and the program would still behave the same. Because remember, in this version up here, I can't just reorder arbitrarily the code. I can't do something like that because the else only makes, is even syntactically meaningful is only in the last position of the con. So this is just meaningless code. And even if I leave the else in the last position, if I swap the null and the EQV test, then I'm going to get an error because I'm going to be trying to take the car of an empty list at some point. So that's no good. Or at least for some inputs, this will give me an error. So that's no good. I need the null test first. Okay, so with the standard way of writing tests, the con clauses have to be in a very particular order. You cannot reorder them, or you will get erroneous results or a syntactically incorrect program. So the first step is we're going to add special tests or modifier tests so that all of our tests are unambiguous. So we already saw this. We can add the not null test. Now just go through all the steps. If ls is not null and the car of ls is EQV to x, then proceed. Okay. All right. And what we talked about also is that we don't really have a not null test in miniKanren. We don't have not in general. We have disequality constraint, which is a very, very weak form of not. But we can't really express not null. What we can do is instead say pair. So this would be sort of the miniKanren way of looking at it. We could say that ls is a pair. So for our purposes, this would be equivalent. So that's a test that is not going to break anything, shouldn't change the way rember works, but is more explicit. And it means that we can swap the clauses and have this clause come before the null clause, and the code will work the same. Add the same test here for else, similar test. Okay, so that's our test for the last one. And once again, we don't really have not. The closest thing we can imagine is we might have something like a not EQV. Okay, so you could imagine defining it as like a little helper. It's two values. Okay. This is a very restricted operator in that it's not a general negation operator. Wrapping not around an arbitrary expression is actually pretty powerful. It's difficult to encode in miniKanren. But we can have something like not EQV, which is a very, very weak operator. And that would actually work just fine. Okay, so we don't need the full power of not. We can do something like not EQV. And once we have this written, now if we wanted to, we could reorder these clauses any way we want. And the program should behave exactly the same as what we had before. Okay, that's the point of adding those sorts of parts. All right, so I'll go back to the original ordering just for readability. Now that we've made that transformation and we can reorder it any way we want, the next transformation we'd make is unnesting. So basically, anytime we have nested calls, we have to pull those out somehow. So here's a call to car that's inside of a call to not EQV, that sort of thing. No good. And actually, the and itself is a perfect example of this. We want to pull that one out. So how do you do it? Well, we do it with let. So things names. Let A be the car of ls. Notice I just replaced the car of ls with A. Okay. So unnested a little bit. What else is left? Well, pair is simple. Only has a variable reference as an argument. A and X are simple. We have the call to A, and though. So if we really wanted to be serious about it, we could say, well, the call the pair is going to return, I don't know, PT for pair test. Okay. And I can say that it's called EQV. Give me ET for EQV test. And I end up with this one hand like that. Okay. So you, at this point, everything's completely unnested. Every single call only takes variable references. There are no nested calls because we pulled them apart with lets. Okay, so we've simplified the code, and in fact, there's something called a normal form, administrative normal form, or ANF, is used in things like compiler transformations, that kind of thing. We basically were rewriting our code something like a normal form. So there's sort of a theoretical basis to what we're doing. And it turns out that the way miniKanren works, it requires something very similar in spirit. Okay, so we're just practicing a little bit here with things in Scheme. All right, so the result, we're returning the coder of ls. That's just a simple call as well. That's, we just have variable reference, so we don't have any more unnesting to do. All right, what about the next pair? Well, or the next test? Well, we have some nesting. We're inside an and. We have a call to car. Same thing. Let's do the same thing. So we always nest inside out. Sorry, unnest inside out. So let's grab the innermost one, the car. That. Okay, pull this out. All right. So now it's unnested except for the call to and. So we can even pull out the test if we want. ET is pair test. And let's see. And we got one more test to pull out. NET is not equivalent test. Okay, so I've unnested now my test completely. Notice that the only arguments to these calls are variable references. Now I can unnest the return expression. So here we've got this call to the car of ls is nested inside of cons. The call to coder is inside of rember, which is inside of cons. So I'm going to do the same sort of thing. So I could, and it doesn't really matter the order I do this. So I could take the coder out first instead of the car because it's nested most. That's fine. Take the car out. Actually, just do it one step at a time to be fully explicit. I take the car out, and now I have to take the rember call out. So now I've pulled out all the pieces parts. I'm calling res as the result of the call to rember. And finally, I have the cons to call, which is the result. And notice that, the final result. Notice that now, for my definition of rember, every single call to a procedure inside of rember takes only variables as arguments. There are no nested procedure calls. I've pulled everything out so that everything's let bound. Okay, all those calls are let bound. And then finally, we have this one call that's in tail position. Okay. So that's this very bizarre looking definition of rember. But metaphorically, this is what you have to do for miniKanren. You have to make sure that, first of all of your tests are independent, which means that we can reorder the tests. Okay, so I've reordered the clauses, and now my base case comes last. And I've also made sure that all of my procedure calls are unnested. Okay, so I've got these two properties that I care about in my definition of rember. So let's just check and make sure that did it right. Let me my rember, and let's see if our tests actually run. Here's the test. I wrote a helper for my not, so let me make sure I've got that as well. Remember, the reason for this helper is to make sure that we don't have to have a full call to not. Our code also doesn't have any calls to not in the actual code. There's a very simple type of negation to say that two values are not equal. That's it. That's the only form of negation we have. All right, so it looks like I did something wrong. So what did I do? Oh, yeah. When I was unnesting, okay, so this is interesting. This is interesting. So I normally don't do this in Scheme. This is normally something I do in miniKanren. But it turns out that there's like we have to be very careful when we do our unnesting to not mess up the order in which our tests happen. So in Scheme, unlike in miniKanren, I have to actually check that ls is a pair before I check, but before I take the car of it. And if you notice that the ordering here, I'm taking the car of ls before I check pair. So I'm getting a little sloppy because in miniKanren, I don't actually care about the ordering. So that's a nice thing about miniKanren programming. So what I have to do is just swap these two let bindings. Dependency there. I have to be careful about that. Let's see if there are any other dependencies. That looks okay. Same thing down here. Okay. Spare test has to come first before the car. So these lets have dependencies in them. So miniKanren, we can get away with being swapping our code around in an easier manner. Okay, did I still screw that up? Let's see. Pair, car, not equal, and pair. Okay, so that should be fine. And here. Oh. Oh, this is awesome. I love it. I love it. This is a happy accident. Okay, so remember how I wanted to unnest the ands and all that. Wow, this is so much more complicated in Scheme than it is in miniKanren. I'm starting to get an appreciation for what we can get away with in miniKanren. This and, that's the problem, is that this and needs to protect things. So that and actually has to come. Oh, so I guess we can't really fully unnest it. That's a little unfortunate. So the thing is, we actually have to check. And here before we continue. We have to make sure that if PT is not a pair, that we're not taking its car. So we have to do a test right there. It's so amazing that in miniKanren you don't have to worry about those things, but here we do. I don't think I've ever actually done quite this transformation in Scheme before. It's much easier in miniKanren, actually. I'd say that. Okay, so we had to pull these ands out. Luis is like trolling me again now. But this is great. This is the best type of trolling. This is the best type of trolling because I'm learning something. Okay, so let me try it now. Okay, now it finally works. No apologies. This is great. I love it. Okay, so we've ended up with this horrible looking Scheme program. Oh, we have to have ands here. It's really nasty. I have to think a little bit more about how else maybe we can rewrite it. But this is, we have to worry about all of these things. We have to worry about the ands. We have to worry about the these pair tests coming before the cars, and The ands have to come in between so to protect us. And there are all sorts of ways we can get in trouble and get errors. And all of this is just to make sure that we can reorder our code in any way we want in terms of the con clauses. But obviously we can't reorder the conjunctions, the ands. That gets us into trouble. So really we're in a very fragile state when we're in a scheme. We really can't mess with any of these orderings without kind of getting into trouble. So you have to do everything exactly right. Whereas in miniKanren's loose enough and the semantics are declarative enough that often we can just swap things anyway. We can always swap things any way we want. The only problem is we might lose something in terms of performance, or we might go in an infinite loop if no answer exists. But it's always safe to do these transformations. It's very, very painful here to do the same thing in scheme. Ugh, I've never written this before. This is pretty horrible. Anyway, so this is to try to give a little intuition as to the sorts of transformations we're doing when we're going to the miniKanren code. So for rember, and actually our version of the scheme code will be far prettier than this thing. But it gives you the idea. So we wanted, there are some properties of scheme code that we just can't depend on in miniKanren because miniKanren is more declarative, and because miniKanren doesn't assume certain orderings, right? So in scheme, you have con and you have a specific order in which things happen. We can't depend on that anymore. So all of those condy clauses get executed independently. They could be parallelized. They could be run on different computers, right? They really are independent. Whereas here, we have to try these expressions in order. That's why we can write things like else. So we have to be way more explicit in miniKanren with the tests. So that's the first thing. And it turns out because of the way miniKanren works, sometimes we can simplify the test, but we do have to be more careful. And then the other part is this idea of unnesting, that we have to pull the nested calls apart. And you can kind of think about that because in miniKanren, we're not returning values anymore. We associate some argument, some argument of a goal with a value. Right? So we actually have to pull things out so that we can do those associations. We can't just have nested function calls like we can in scheme. This is, by the way, sort of an open problem. Is there a way for us to simulate the nice syntax of these nested calls and still do it in a way that makes sense? And I don't really know how to do that. It'd be nice to be able to just write things like that. One approach is you could write a scheme to miniKanren compiler. You could also, of course, run rember in the relational interpreter. That gets around the problem in a different way. But if you're going to write this in plain miniKanren, you just can't have nested calls in the same way. Okay, so that was a bit of a jawbreaker. We ended up with this horrible, horrible looking thing that I couldn't even write correctly the first 2 times. I kept messing up. And when we actually end up with our final rembero, we should go back and look at the scheme rember, and actually, rembero will look really clean compared to this, and it'll be much more flexible too, of course. Okay, so what I was trying to motivate was why we had to do the unnesting step, right? So if we go back and look at kind of the original rember. So first of all, we had that else test, and so we've kind of encoded that, the equivalent of the else test by saying that ls has to be a pair and then x and a have to be different. Okay, so that's the equivalent to the else. We had to be more explicit, the equivalent of Dijkstra guards, but that's fine. That was the test part. That's done. Now we have to encode what in rember would have been the return value, and that's where that unnesting step comes in. That's critical. So we're going to do something similar where we have to pull out the different parts. So when we did in scheme, we had to pull out the car of ls, the coder of ls, let bind those to a and d. Fortunately, we already get that because we did fresh ad and we unified ls with a.d. So we already have a and d laying around. So we don't have to take cars and coders. In fact, we can't. We know we can't take the car of ls. We can't take the coder of ls because those ls could be a logic variable, right? We're being more general, which means we have to be more careful about things. So this D, so this coder of ls is basically D. in our world, and this car of ls is basically A for us. Cons we know is safe, that's fine. We can take cons, we can cons things up. We can make a recursive call to rembero, okay, but we can't have the recursive call to rembero inside of the cons. That's no good. So we have to pull that out. So if I were to take the scheme code from rember and plop it in here, we would immediately start having to do some transformations. The car of ls, that's what we're calling A right here. The coder of ls, that's what we're calling D. But the rember call is wrong. It's nested inside of a cons. That's not something we're allowed to do. And also, we're calling rembero, not rember. And rembero takes 3 arguments, not 2. So it's different. So if we want to think about this in terms of taking the scheme code and massaging it till we get the miniKanren code, that's one way to think about these transformations. So rember becomes rembero. We have x and d. Those arguments are fine, but we need the equivalent of our third argument, the equivalent of our output argument, or the ls-x. Okay, what would that be for rembero? Well, that's some sort of temporary value I call result. Add that to the fresh, fine. And now we're going to cons A to result, because we use the cons A to the call to rember. By unnesting, we need to give a temporary name. So this is sort of like the let binding. We let bound res to be the result of the call to rember. We're doing the same sort of thing here. And then, of course, we don't have the notion of returning a value. We're not returning the value of cons A res. Instead, we have to associate cons A res with our new output value, if you want to think of it that way, ls minus x. So that is what we would end up with. Okay, so that's the definition. Now, of course, we've learned or talked about how we want to have all the calls to equal or not equal come before the call to rembero, because rembero is recursive. So we would probably reorder them and end up with something like this. So this is a rember-o definition, which I believe is correct. Res is in effect the coder of ls-x. Yes, that's right. So we can even see that. I think I called it res here. So when I did the unnesting in this horrible scheme version, I pulled out rember, the call to rember, and I named it res. And you can see I conned A to res. And you can see that we're doing the same sort of thing in rembero. If I go back to the original ordering, that we have cons A to res, and here we had cons A to res. And wherever we return something in scheme, in miniKanren, we would do the equivalent of unifying that value with our output argument. Okay, so the code is actually very similar. So we had this called rembero xd res. Well, up here we have rember xd, and now it takes a third argument in the miniKanren land, and the third argument is equivalent to res. So the structure is actually very similar. You can see we're taking cars and coders, we're calling those d's and a's, and of course that's really what we're doing here. We're taking cars and coders, calling those a's and d's. So the structure is very similar. And if you look at the scheme code and really understand what's going on with the scheme code, and you look at the miniKanren code, you can really see a lot of similarities. Okay, so that's what we're doing. And here is a definition of rember-o. In fact, we could probably even simplify the definition of rembero, but you can see that definition of rembero, let me zoom out a little bit, split screen. You can see that this definition of rembero is far shorter and less complicated than this definition of rember that we've transformed the different ways. So it is true that compared to the original definition of rember, our definition of rembero is somewhat longer, but if you think of the sorts of transformations you'd have to do to rembero to make it, or sorry, to rember and scheme to make it equivalent in terms of being able to reorder clauses any way you want, and the unnesting, you would end up with this horrible beast. And even just doing the Dijkstra guard version, which is right here, you can see is almost as long as the rember-o version. It's about the same complexity. So, we're trying to be more general, So it's not really fair in some sense to miniKanren to compare it to the direct style version of rember in some sense, because in rember you can't reorder the clauses, that kind of thing. So we gain some extra flexibility, but it means that we have to be more careful. Okay, so we have rember-o. Let's try rember-o out. So let's try a run query. Let's make sure our miniKanren is working. I forgot to load the file. Let me just load the file. We'll move the old stuff down here. Just load the file, which is the right way to do it. Load Hangout 9. Great. So let me try run. Great. And now let's try doing a rember-o. We can try rember-o on one of our tests. So rember-o x to this one. Remember, we have an output argument now, or a third argument, the ls minus x, or whatever we called it. And we get yzx, which is what we expected. So that's this case right here. So that's good. So that one worked. And now we can, of course, start playing interesting games where we run it backwards and so forth. So let's put the let's put in the expected output. So that's fine. It means it's consistent. That's why we get an _0, saying that q could be anything. And of course, now we can put q in the middle, right? So we can say, give me a list where if I remove the first occurrence of x from that list, I get back yzx. And so miniKanren gives us actually our list that we did for the previous example, x, y, zx, but we can ask for a second answer. And yeah, that one's true too. I thought it'd give us a different answer. But if you have the list yx, zx, then if you remove the first occurrence of x, sure enough, you get yzx. So it's third one, yzxx, that's right. Let's see if it comes up with anything else. Oh. So really only 3 answers? Oh, there are only 3 answers. I thought there were infinitely many, but there are only 3. Okay. Interesting. Okay. Wow. Okay, that's really funny. I thought there were infinitely many answers, but there really are only 3 answers. Great. I love it when miniKanren is smarter than I am. Why did I think there were infinitely many answers? Well, I was thinking there were infinitely many answers because I thought I could keep adding, things like, I thought it would give us answers like x _0 _1, yz, and it have some side condition saying that, _0 is not equal to, x and stuff like that, right? I thought those were the sorts of answers we can get, but of course that's no good because since it's only removing one x, the list would be longer than 3. So there really are only 3 answers in that case. Oh, great. Okay, that's kind of fun. Yeah, exactly, because we only remove 1 x. So if we removed multiple x's, then we could actually get infinitely many answers and that sort of thing. Okay, and of course, we could play all sorts of other games, right? So we could say x and y. So what are all the x, y? Okay, so here there's still finitely many possibilities. So here I'm asking, what are all the symbols and lists, that you come up with? So if you move some symbol _0 from, actually we didn't even enforce that it's a symbol, but if you move some value _0 from the list that begins with _0, and then yzx, you'll get back yzx. So this is sort of a generalization of that. Okay, so you can do all sorts of fun sorts of tricks with this. I want to show you at least one more thing. So, could we define rember-o a little bit differently? Or are there any other simplifications? So let's go back to something we had a little bit before, where we wrote something like that. Okay, so if you remember, in the second case, we originally had some code like this saying that we break ls apart to the pair a.d, and then we're asserting that x and a are the same. And just said that that's not strictly necessary. We could replace the a with x and then remove the variable a and get rid of this line. We could do that, and that's fine. However, if we keep the original version like this, then we might notice that there's some shared structure. So in this case, we're also doing exactly the same unification with ls. And here this nice symmetry now, where here we're unifying x with a, and here we have a disquality constraint. So this is maybe more symmetric. And in fact, if we really wanted to kind of refactor this code a little bit more, and we could even do something like, let's refactor it so that we have a fresh AD, because both clauses are going to have that. Maybe we can combine the clauses. And then the first thing we can do is this unification. And now we can have a nested condi as two clauses. And in one of those condi clauses, we are unifying x with a. And in the other condi clause, we're saying x and a are not the same. So I can pull that one out. And so these are tests. Okay. And in the first case, then we're going to unify ls dash x with b. So that gets rid of that clause entirely. Let's see. And in the other case, what has to happen? Well, we already have a and b around. So basically, we just take the resulting code here. And I think that's right. So let's see. How's this work? Let me reformat it like that. So basically, what we said is that in those two condi clauses at the end, in both cases, we're tearing apart ls, and to get the a and the d. And in one case, we're saying that x and a have to be the same. In the other case, we're saying they have to be different. And in the case where they're the same, we already have the d, and we already have ls minus x. So just unify those. And in the last case, we have to introduce this fresh res argument so we can make the recursive call, and we have to make this other unification, but all the other variables are already around. So we can combine those clauses. So this would be another way to write rember-o. And just to keep ourselves honest, running that scheme code, let's just make sure that it really does behave the way we think it will. Yep, get the same three answers. Great. So I guess the point here, code a little smaller so we can compare it. The point here is that with the miniKanren code, there are lots and lots of ways that we can write same code, lots of transformations we can make. So here's the version with the nested condis and the shared use of the logic variables a and d and the shared unification of ls to a.d. And here's where you break the clauses apart individually, and you have some redundant computation, but this clause gets a little simpler. So which one do you prefer? That's up to you. That's a stylistic choice. They mean the same thing. If you really cared about performance, you could try benchmarking and stuff like that on different queries. But for now, we're concerned about performance only at the level of, does this go in an infinite loop when there is no answer, that kind of thing. And in this case, they're the same because the recursive call is at the end. It's in tail position. So that's another way we could write rembero. Now, if you want a little bit of an exercise to try on your own, what I would suggest is instead of rember, I'll put a little exercise here. You could define rember, multi-rember is what Dan calls it in the little schemer, which removes all occurrences of X from LS. Okay. Instead of just removing the first occurrence, it removes all of them. And then, so that's part one. And then, of course, part two is define multi rember-o in miniKanren. You don't have to go through all the steps we went through with, transforming the scheme function to make it use Dijkstra guards and to do all the unnesting. If you find that helps, you can, but you don't have to. It's a good exercise to try, but it's not necessary. But you're going to have to do the equivalent in miniKanren. And of course, you can start with rember-o. That's most of the way there with multi-rember. And then if you want to try something even a little bit more interesting, you can define rember star, which removes all X's from a deeply nested list or tree. Okay, and we did this in Scheme when we were playing around with Scheme. We saw how you could add a special pair of Kutter tasks, or sorry, pair of the car of is the car of the list a pair type thing, and that gives you a deep recursion. So basically, rember star is like the deep recursion, and then you can define rember star-o. You can do the deeply recursive relational version as well. So those are a few exercises if you want to practice up on this a bit more. So what else? Well, let's do one more thing. Let's yeah, this will be fun. So here's what I want to do. In the past, we've written parsers for expressions. So we wrote a parser for scheme expressions, just using pmatch that will take a scheme expression, and it's basically going to return #t if the scheme expression is legal for our language, and it's going to return #f if it's not. It's just like a little predicate. And we define like a little grammar, I think, for our language. So we said like lambda might look like have a pattern like this, right? These sorts of patterns, and you can have lambda calculus where you have x as a symbol, and that's representing a var, right? This is a variable, and this is lambda or abstraction. And then we could have application, which is like rate or band, or E1, E2, this kind of thing. Two expressions there, and that's our application line. That can, and of course we can add lat and latrec and whatever else we want. Okay, so we wrote a little parser, and so let's write a little parser in miniKanren. Okay, and let's just write it directly. We've already done some examples where we take scheme code and we translate it to miniKanren, but let's just write this directly. using kandi and equal and all that. So let's call it parseo. Down. Okay. Well, oh, sorry. How about we have a lambda? That'd be a good idea. We're going to have, whoops. We're going to have some expression, expert, right? And we can treat this as a predicate where parseo will either succeed or fail. That'd be one way to do it. Or we can have an explicit #t#f, where if it parses correctly, we get back correct expressions, and if it doesn't parse, then it doesn't. I don't know. Let's just do the version that succeeds and fails first. So we have these different expressions, so we have to figure out how to handle those. So let's start with lambda first, because that one has the most structure. So in some sense, this may be easiest to do. So let's do lambda. We unify lambda x body, or I guess maybe we call it e. E is some expression. Well, x and e are fresh logic variables, so we're going to have fresh xe. And now we're done. Well, not quite, because e is an expression, so that means we have to recursively parse it. Now, what about application? Well, so what does an application look like? Expression E1, E2. So therefore, we need a fresh E1, E2. And it's a similar sort of deal where we now need to parse things. Parse E1, parse E2 recursively. Notice that we have two recursive calls in the same conjunction. So there's no way to put them both last. So we have to pick which one we want to parse first and which one to parse last. So I'll just use this ordering. But this is already trouble. This is how you get into trouble, is when you have two recursive calls in a conjunction. They can't both come last. So our rule about having the recursions come last is not something we can achieve in that case. All right, fine. We got an application. We've got a lambda. And we want to have the variable case. So we have some x thing, a symbol. Well, how do we represent that? Well, we could have like some sort of tagged variables, I guess. We could say we have a tag list. And we say this is a var and it's x or something like that. We could have tag variables, and we certainly could do that. In fact, we could also tag application if we want. We could have an app tag on application. It's not very schemely, but we could do it. We could tag our variables as well and have a fresh x, and, that kind of thing, and just say, hey, we succeeded because we have a variable. And that works, and you can totally do it. And we did that for years. I don't do that anymore. Because the reason is I want the code that I'm generating and manipulating to read exactly like the scheme code that I work with. So instead of using tagged application and tagged variables and all that, basically over the years, we've come up with techniques where we can avoid the tagging. So one way you can avoid the tagging is to say, well, what you would say in scheme if you're writing an interpreter is you would say that the symbol is an expression. Okay, we do something like that. But we don't have symbol question mark in miniKanren, and symbol question mark wouldn't work if expression were a logic variable, something like that. So what we've done is we've created a special constraint called symbolo, or however you want to pronounce it, that behaves metaphorically like symbol question mark. So in scheme, And we can quote a symbol like foo or quote dog or whatever. And you have a symbol question mark. Symbol, but 5 is not, that kind of thing. In miniKanren, we have something similar. Symbolo, cat, that succeeds. Symbolo of 5 fails. May as well go ahead and tell you that we also have something similar, which is rember-o. Rember-o of 5 succeeds. Rember-o cat fails. And of course, we have other things like errors. That's going to fail for rember-o or for symbolo. So symbolo and rember-o are these useful constraints that are similar to symbol question mark and number question mark. They're like type predicates in the scheme. And these are the little constraints we can use in miniKanren. So I'm going to say that the expression is a symbol, and if that's the case, we're going to treat it like a variable. Okay, and then we're done. And in fact, if we want to get into that business, we can also say that X had better be a symbol. That identifier had better be a symbol. So this is how I might write a simple version of parseo. So let's see how our parseo works. So let's load it. Let's give it time to parse X. Parses about 5. 5 does not parse. How about lambda y? That parses. How about lambda y5? That fails to parse. How about lambda y z or z y? That fails to parse because our lambdas only take one argument. Okay, great. So that seems to be working. How about an application? How about lambda yy applied to itself? Yep. How about 3 times? Nope, doesn't parse because our application only allows 2 expressions. Okay, so our parser seems to be working and accepting things. So now, of course, we can play our famous game of putting in a fresh logic variable. And now what we're going to do is use parseo to generate expressions that parse. These are syntactically correct expressions given our simple language or grammar. So the first thing we can get is this answer has a side condition or constraint, just like we'd have side condition for disqualifying constraints, saying, okay, basically the expression can be anything as long as that thing is a symbol. So this is a representation of any possible symbol. So it could be the symbol cat, dog, foo, whatever you want, X, Y, Z. So that's the variable case, any particular symbol. Great. Second case. Okay, so this is sort of an abstract version of a lambda expression. So saying that, all right, we can have a lambda expression where the identifier is a symbol, because we have the side condition, and the body is also a symbol. So this is some sort of variable reference. So that would be, something like lambda yz or lambda yx or something like that, or lambda yz would be syntactically valid. Okay, it doesn't matter that this identifier is occurring free. It's still syntactically valid according to our language. Okay, so this has to be an identifier basically, or a variable, and this is an identifier. So that's and notice that this refers to infinitely many expressions. You can put any symbols you want in there, and it's legal according to this grammar. So I could put cat and dog, whatever. That's fine according to our grammar. It's a very succinct way of expressing infinitely many answers. The third case, we have an application, and the application is of 2 symbols. So this would be like X applied to Y. Okay. Let's Right. Okay, so those are our three types of expressions, basic types. We have a symbol representing a variable. We have some application. We have some application. Or sorry, we have a lambda and an application. So now we're going to start getting combinations. So this is a nested lambda. Whoops. So these are all symbols. So this would be like lambda x, lambda y, z. Now, these symbols don't have to be different. There's no side condition saying they have to be different. So this would be one, would be x, y, z, where they have nested lambdas. These could also be x, x, z, or even x, x, x. Those are all would all be legal according to that answer. And here's another application and so forth. So let's I don't know, let's let it run a little bit. What's 100? Okay, so you can see we've got this one is, these are all symbols. So I guess only having symbols in our language means that the lambda calculus thing means that we're not going to have a whole lot we can play with other than variables, of course. But just kind of fill things in. This would be T and this is S or something like that. So this is an example of a term that's well-formed. This is a well-formed expression in our language. Okay. Of course, if we go back, we can add other things. So if we wanted to, we could add numbers. So we could say rember-o. So now we'll be allowed to have numbers as well. What else might we want to have? I don't know. Maybe we want let. So we could add let as well. Let. And unify let expression with expr. So x and some e and some body, and we'll go ahead and say that x has to be a symbol. And of course, we have to recur. Now here we have to recur on both e and body because those are both. We have to recur on those. Okay. Let's try it again. So let's do like 5. Okay, so we have the number case now, so that could be like 5 or 137 or something. Let's see if we can hit a let expression. All right, well here we got a couple let expressions. So let's pull this one up. So this let expression, we have the side conditions says that 1 and 2 are numbers, and that _0 is a symbol. So this could be like z, and this could be 5, and this could be 132. Okay. So that would be a legal let expression. Sure enough, fine. And of course, I can run that in scheme, and it actually works. So here we got another let. Pull that one out. What's going on here? This is saying, according to the side condition, that right has to be a number. So I'll say that's 7. And the others are simple. So this might be like x, and this would be like y. Or I could actually, so this could be like y, or it could be the same symbol. That's allowed too. So in this case, it's going to run. And if I make it y, then we'll get y is not bound. Okay. So those are expressions there. And we're not paying attention to an environment with this parser. So shadowing is not allowed. We're not really taking account of things like shadowing. So in this interpreter, lambda is always lambda, that kind of thing. So let's see. All right, so let's do one more variant. I think we'll call it a day. So let's write a version of parseo that instead of just succeeding or failing is going to take as a second argument, either a logic variable or a flag that's going to say whether or not this expression is legal. Okay. So now we have something sort of like an output argument. And if we have a number, that's legal. If we have a symbol, that's legal. If we have a lambda, so now when we do the recursions, we pass that flag down. And if all that happens, oh, so let me think about that a second. So we want to be able to do illegal things also. That's the point of this, is we want to be able to do illegal things. So in this case, a number is a legal expression. A symbol is a legal expression. This lambda expression is legal. So are there ever any cases, I guess, unless we have illegal expressions, maybe it gets tricky. So, oh, okay, I know what to do. All right, here's I guess how to do it. We probably actually need some expressions that have like errors and things like that to make it more interesting. So let's see. I don't know. Maybe I'm not sure what the best way to do this is. If you have an idea, let me know. Here's one thing that comes to mind. It might be not so great. So if the recursion is legal, then the whole thing is legal because that lambda is legal. So that part is true. If the recursion is illegal, then this entire expression is illegal. Because the lambda structure is legal, but the body isn't. Okay, so that's one way to do that. We might have to add some illegal things, illegal expressions to make it more interesting. Well, let's get rid of let for now. I don't care about that. And then care about application. So for application, I guess it's the same sort of thing, right? So oh, okay. So let's see. I guess here, both E1 and E2 both have to be legal in order for the whole thing to be legal. So if those are both legal, then the whole thing is legal. And if the first one is illegal, then we're illegal. We don't even care what the second one is. And then was the third case, if the first one is legal and the second one isn't, then we're also illegal. Okay. I think that's all fine. The only problem is that we don't yet have any expressions that are going to be illegal. Like we don't have any base cases that are illegal. So I guess one thing we could do is say we want to have just like really simple lambda calculus-y things, and we don't have numbers. Okay, so we're going to say numbers are now illegal, and we only want lambdas, let's say, that have one binding. Okay, and so if someone has a lambda that doesn't have one binding, maybe we want to treat that as illegal. So maybe we'll add another case here. So maybe, lambdas actually that don't take any arguments are illegal. And maybe lambdas that take too many arguments are illegal. So let's see, how would we, the best way to do that, I guess, if we had something like x, y, z star, something like that, I guess. So maybe it's not even a proper list, or maybe it has two bindings or more. That should be fine, and then it's not legal. So let's see, is that good? And for these, we don't have to recur because they're not legal expressions. Huh. Let's see if I get that basically right. Do a little parseo. We want to say we want expressions that parse. Okay, so we have to feed in the flag now. So those look like legal expressions, and we can also make the flag the logic variable and say we want to see if lambda z y parses, and it should. Sure, great. And what about lambda z w? That should not parse, so we get false. Great. And now the fun part, of course, is that we can say generate 5 illegal expressions. Let's see what we got. So numbers aren't legal. Lambda with 0 arguments. Lambda with 2 arguments dot something. So this is a general case. Let's see, what is this? This is a legal lambda that has a number in its body. We have a number that's part of the application. Yeah, we don't, I guess in this case, we don't even particularly, I guess if we want to fully ground it, maybe we should do the recursion. So let me just, yeah, I guess the interesting thing here, oh, this is kind of fun. The fun part here is that when we should really recur probably. So we get ground values. And when we recur, we can, it doesn't really matter if it's legal or not legal for the sub-expression because we already know we're illegal. So we can do this thing where we're kind of like, all right, from this point on, we don't actually care. That's kind of fun. And all the cases there. Yeah, so here, we should parse E2 in the same way. Parseo. I think that's parseo. I think we'll get more interesting answers from this. Let's see. Let's take a look. All right, so now we're getting ground here. So yeah, so a lambda of no arguments, the symbol is a body or a number is a body. Let's do 10. What's this thing? So here we have syntactically correct lambda, but the body has a num. Okay. Here we have nested sub-expressions. And so I guess one of the interesting things is that something be legal. So in here, the body of this lambda is perfectly legal. It's a symbol, but the number of arguments is wrong. We could also relax this thing right here. So instead of having a dot, we could try generating the lambdas of various number of arguments, that kind of thing. But anyway, that's a little parser where you can generate legal and illegal expressions. And of course, you can also leave both arguments fresh. So now it's going to generate a mixture of legal and illegal expressions, and it's going to tell you for each one. So I'm just kind of curious what it's going to come up with. Is it going to come up with mostly legal expressions or illegal, or is it going to? So most of these are actually illegal. That's kind of interesting. So maybe maybe it's easier for our system to generate illegal things. Okay, so here's something legal, but illegal, illegal, illegal. Most of these are illegal. A few legal expressions. So that would be another exercise, is to play around with something like parseo, either the version that has a flag or it doesn't, and try adding an environment to it so you can handle shadowing, or try adding other forms like let and let rec and so forth, and then see what sort of things, what sort of programs it can generate. Is there anything, is there anything you can generate that's interesting? Maybe you could use something like this for fuzz testing. What if you're going to use it for testing? You probably need to have what's called a grounder. You probably need the ability to take something like _0 in the output, where _0 is a number, or _0 where _0 is a symbol, and generate automatically some numbers and symbols to fill that in, so you can actually run all of the programs in Scheme. And you also might, at some point, care about making sure that your expressions don't have free variables. That's something you could also add as well if you wanted to. And you can already see that we're starting to sneak up on the relational interpreter, because writing a parser is starting to get pretty close to this. And so we'll have patterns like this where we have numbers and symbols representing variables. So we'll have to do environment lookup and match on lambdas and so forth, and doing recursion. So this is already starting to get pretty close to a relational interpreter. The relational interpreter will be much more interesting, both in writing the interpreter and also in terms of its behavior, especially running it backwards and that kind of thing. So we're starting to get close. We'll be able to do that. And notice that also, it was pretty easy to write this just directly. I didn't have to write it in Scheme first and translate it. Kandi with equal works a lot like pattern matching. So I could just write down one clause for each of the expression types. Luke says this is already really cool. Yeah, it is pretty cool. I mean, if you wanted to write a program to generate legal and illegal expressions, however you did it might be more complicated than this. But we can easily add more behavior. We can easily add environments and stuff like that. And the code is actually pretty succinct. If we actually used there is a miniKanren equivalent to pmatch. So if we wrote it with that approach, it would even be shorter. And then, well, you'll see soon. Like when we really get into adding behavior, it'll be much more interesting. And also, if you write a type inferencer has a lot of similar structure. So we're already getting pretty close now to writing the really fun stuff. So I think that's plenty for today. I don't know, maybe next time we'll write a little interpreter. I mean, we already have enough in our heads now to write at least simple interpreters. And so probably next time we'll write at least a simple relational interpreter, just to get started thinking about that. And we have to write environment lookup, that kind of thing, but it's not that hard. We've already written environment lookup a bunch of times. It's simple in miniKanren. It's actually quite simple. If you have disequality constraints, that was kind of the key thing. You need something like disequality constraints. Otherwise, you get bizarro behavior. Yeah, so we'll do that next time, and that's when it's really fun. I mean, the relational interpreters, that's probably the most fun I've ever had programming. That's you can just go so many different ways with them. And just like I was getting surprised with that stupid was it rember-o program, right? I mean, that one surprised me. Had I thought about it a little longer, it wouldn't have surprised me, I guess. But even with a program that simple, I can get surprised. And when you try the interpreter, that is full of surprises. So doesn't take very much to write a program that's really hard to predict all the secrets it has. So we'll do that next time. Play around with relational interpreters, and from then we can start exploring really fun, deep things, and we'll be getting pretty close to the state of the art for miniKanren research, and even starting to touch on some open research problems. So that was going to be exciting. Okay, so that's for next week. Starting to get into relational interpreters. I'll end the broadcast now. If anyone wants to talk for a minute, that's fine. Otherwise, I'll get some pizza. Talk to you all later.